Okay, I've got an initial value problem up on the board. This time this corresponds to an undamped harmonic oscillator. So here the y prime term is 0. But once again, we've got impulse forcing being modeled by the direct delta function. In this case, it's just one copy of the direct delta function at time 2. So we shall apply Laplace transforms to both sides. And I know the Laplace transform is linear, so I can just take the Laplace transform of each term and I can factor out any constants. I'm going to, as usual, just do some side work for the Laplace transform of that second derivative. Okay. So I know that's the Laplace transform of the derivative with respect to t of y prime. And by formula 11, that's going to be s copies of the Laplace transform of y prime minus y prime at 0. And y prime at 0 is actually just 2. So I've got s copies of the Laplace transform of y prime minus 2. Now I'm going to apply formula 11 again. So I've got s copies of, this will be s copies of the Laplace transform of y minus y of 0, and then still minus 2. Y of 0 was 1. So I'm going to do two things here. I'm going to distribute the s and replace that with its value of 1. So I'm going to get s squared Laplace transform of y minus s times 1 is just minus s minus 2 is what we get. Yes. Okay. So I can now replace this with s squared times the Laplace transform of y minus s minus 2 plus, now I'm going to apply the Laplace transform here, so I'm going to get 9 copies of the Laplace transform of y. And the Laplace transform of the direct delta function at 2 is just e to the negative 2s. And that is a formula. I want to say formula 10. It is formula 10. Okay, excellent. So I'm going to do two things in the next step. I'm going to add over, I'm going to add over the s and the 2, and I'm going to factor out the Laplace transform of y from the other two terms. So we'll have the Laplace transform of y times s squared plus 9 is equal to e to the negative 2s plus s plus 2. So the Laplace transform of y is going to equal e to the negative 2s over s squared plus 9 plus s over s squared plus 9 plus 2 over s squared plus 9. All right, I'm going to just recopy that at the top of the board, and then we'll spend a little bit of time doing some algebra to try to make it an exact match to some of our formulas so that we can apply the inverse Laplace transform. So as I copy that, I'm just going to write that e to the negative 2s off to the side, and it's times 1 over s squared plus 9 plus s over s squared plus 9 plus 2 over s squared plus 9. And since I've cleared all of this space, I think I'm just going to reserve this little portion of the board here. I'm going to copy down the relevant formulas from the formula sheet that we're going to need. So I'm going to need formula 14, which says that the Laplace transform of the Heaviside function times a translated, horizontally shifted function is just e to the negative as times the Laplace transform of y. I'm going to be using that here because I'm multiplying e to the negative 2s by this, which I'm hoping is the Laplace transform of some recognized function. And then the other formulas that we're going to need are formula 2, which says the Laplace transform of sine omega t is just omega over s squared plus omega squared, and formula 7, which says that the Laplace transform of cosine omega t is equal to s over s squared plus omega squared. Okay, some of these have restrictions on S. I'm not concerned about the restrictions on S. At this point, I'm concerned on making them match. Where the restrictions on S are important, however, is if you're deriving the formulas. If you're deriving the formulas, I do expect you to state the restrictions on S. Here, we're assuming that we're working in the domain of this Laplace transform. Okay, so I think I'm just going to work backwards because these are the easier pieces here. Here, I've got s squared plus 9. 9 happens to be 3 squared. And I have just a number on top. That looks like this, although here, if I'm trying to use formula 2, I'm going to want my omega to be 3. So I don't want the 2 on top, I want a 3 on top. But I can rewrite this piece, pull that 2 out, multiply by 1 in the form of 3 over 3, and I get 2/3 times s over s squared plus 9. Now that's a match for formula 2 with omega equaling 3. Okay. This, s over s squared plus omega squared, it's a perfect match for formula 7, where my omega once again is just 3. Okay. So no need to revise that one at all. I'm perfectly happy with that one as it is. Okay. This piece, I've got the same s squared plus 9 on the bottom. I've got just a number on the top, so I want to make it match formula 2. Okay. So this is going to match formula 2 with omega equaling 3 if I multiply by 1 in the form of 3/3. So I'll have 1/3 times 3 over s squared plus 9. Still, it's being multiplied by e to the negative 2s. And what that's going to mean is that, I've got to use formula 14 as well. I've now said I've got here, this is the Laplace transform for sine of 3t, but because I'm multiplying it by e to the negative as, that's going to introduce a heaviside function at 2 and have me evaluate that function shifted 2 units to the right. So now I can say my y is the inverse Laplace transform of 1/3 e to the negative 2s times 3 over s squared plus 9 plus s over s squared plus 9 plus 2/3 3 over s squared plus 9. So the inverse Laplace transform is linear. I can go one piece at a time and factor out any constants. So I'm going to get 1/3. The exponential function here introduces the heaviside function when I take the inverse Laplace transform, and means that when I take the inverse Laplace transform of this, which we said was going to be just sine of 3t, I'm shifting that, so it's sine of 3 times t minus 2. This piece we said was a match for formula 7 for cosine omega t with omega equaling 3. So that's just going to be cosine of 3t, and this is 2/3. This was a match for formula 2 sine omega t with omega equaling 3. So 2/3 sine omega t. So again, here's my natural response. This is my forced response. Now notice what's happened here is, again, we applied the heaviside function at 2. So the forcing function wasn't on until time 2. It gets turned on at time 2. Okay. Now, when we had a damped harmonic oscillator, what we saw was that we got a sinusoidal response, but its amplitude diminished over time because we were multiplying by an exponential decay function. Here, I'm just getting a sinusoidal response. It doesn't die off over time, and that kind of makes sense because there were no damping forces. So this is just turning on that response to that force that we have. So it does seem in both the case of an undamped and a damped harmonic oscillator that our definition for the direct delta function does lead to something reasonable. By having that direct delta function, the Laplace transform, be that e to the negative as, when we then apply the inverse Laplace transform, we get this heaviside function. So we're turning on the response to that force, because that force only happens at that one moment in time. Okay? But the effect of that force might last for a while, but it gets turned on at the time that that force is applied.